let's explore the scientific method, which at first might seem a little bit intimidating, but when we walk through it, you'll see that it's actually almost a common sense way of looking at the world and making progress in our understanding of the world and feeling good about that progress of our understanding of the world. So let's just use a tangible example here, and we'll walk through what we could consider the steps of the scientific method. And you'll see different steps articulated in different ways, but they all boil down to the same thing. You observe something about reality, and you say, well, let me try to come up with a reason for why that observation happens, and then you try to test that explanation. It's very important that you come up with explanations that you can test, and then you can see if they're true, and then based on whether they're true, you keep iterating. If it's not true, you try to come up with another explanation. If it is true but it doesn't explain everything, well, once again, you try to explain more of it. So as a tangible example, let's say that you live in I don't know, northern Canada or something, and let's say you live near the beach, but there's also a pond near your house, and you notice that the pond tends to freeze over sooner in the winter than the ocean does. It does that faster, and it even does it at higher temperatures than when the ocean seems to freeze over. So you could view that as your observation. So the first step is you're making an observation. Observation. In our particular case, it's that the pond freezes over at higher temperatures than the ocean does, and it freezes over sooner in the winter. Well, the next question that you might want to, or the next step you could view as a scientific method. It doesn't have to be this regimented, but this is a structured way of thinking about it. Is, well, ask yourself a question. Ask a question. Why does... So in this particular question, or in this particular scenario, why does the pond tend to freeze over faster and at higher temperatures than the ocean does? Well, you then try to answer that question. And this is a key part of the scientific method, is what you do in this third step, is that you try to create an explanation. But what's key is that it is a testable explanation. So you create a testable explanation. Testable explanation. And this is kind of the core, one of the core pillars of the scientific method. And this testable explanation is called your hypothesis. Your hypothesis. And so in this particular case, a testable explanation could be that, well, the ocean is made up of salt water, and this pond is fresh water. So your testable explanation could be salt water has lower freezing point, has lower freezing point, lower freezing point. So it takes colder temperatures to freeze it than fresh water, So this right over here, this would be a good hypothesis. It doesn't matter whether the hypothesis is actually true or not. We haven't actually run the experiment, but it's a good one because we can construct an experiment that tests this very well. Now, what would be an example of a bad hypothesis, or something that you couldn't even necessarily consider as part of the scientific method? Well, you could say that there is a fairy that blesses, that, let's say, that performs magic, performs magic on the pond to freeze it faster. Freeze it faster. And the reason why this isn't so good is that this is not so testable, because it's depending on this fairy, and you don't know how to convince the fairy to try to do it again. You haven't seen the fairy, you haven't observed the fairy, it's not based on any observation. And so this one right over here, this would not be a good hypothesis for the scientific method. So we would want to rule that one out. So let's go back to our testable explanation, our hypothesis. Salt water has a lower freezing point than fresh water. Well, the next step would be to make a prediction based on that. And this is the part where we're really designing an experiment. So you could just view all of this as designing, let me do this in a different color, where we want to design an experiment. Design an experiment. And in that experiment, let's say, and let's see, the next two steps I will put as part of this experimental. Whoops, I messed up. I did my undo step. So the next part that I will do is the experiment. And there you go. So the first thing is, we'll say there's all sorts of things that are going on outside. The ocean has waves. Maybe there are boats going by that might potentially break up the ice. So I just want to isolate that one variable that I care about, whether something is salt water or not. And I want to control for everything else. So I want to control for whether there's waves or not, or whether there's wind, or any other possible explanation for why the pond freezes over faster. So what I do in a very controlled environment, I take 2 cups. I take 2 cups. That's 1 cup and 2 cups. And I put water in those cups. And let's say I start with distilled water, but then this one stays. The first one right over here stays distilled. And distilled means that through evaporation, I've taken out all of the impurities of that water. And in the second one, I take that distilled water and I throw a bunch of salt in it. So this one is fresh, very fresh. In fact, far fresher than what you would find in a pond. It's distilled water. And then this is over here, this is salt water. So you wouldn't see the salt, but just for our visuals, you depict it. And then we would make a prediction. We'd make a prediction, and we could even view this as step 4, our prediction. We predict that the fresh water will freeze at a higher temperature than the salt water. So what prediction, let's say the fresh freezes at 0 degrees Celsius, but salt doesn't. Salt water doesn't. Salt water doesn't. So what you then do is that you test your prediction. So then you test it. And how would you test it? Well, you could have a very accurate freezer that is exactly at 0 degrees Celsius, and you put both of these cups into it. And you want to make sure that they're identical in everything, where you control for everything else. You control for the surface area. You control for the material of the glass. You control for how much water there is. But then you test it. And then you see what happened from your test. You leave it in overnight. And if you see that the fresh water has frozen over, so it's frozen over, but the salt water hasn't, well, then that seems to validate your testable explanation, that salt water has a lower freezing point than fresh water. And if it didn't freeze, well, it's like, okay, well, then maybe or if there isn't a difference, maybe either both of them didn't freeze or both of them did freeze, then you might say, well, okay, that wasn't a good explanation. I have to find another explanation for why the ocean seems to freeze at a lower temperature. Or you might say, well, that's part of the explanation, but that by itself doesn't explain it. Or you might now want to ask even further questions. Well, when does salt water freeze? And what else is dependent on? Do the waves have an impact? Does the wind have an impact? And so then you can go into the process of iterating and refining. So you then refine, and iterate on the process. When I'm talking about iterate, you're doing it over again, but then based on the things that you've learned. And so you might come up with a more refined testable explanation, or you might come up with more experiments that could get you a better understanding of the difference between fresh and salt water. Or you might try to come up with experiments for what is it about the salt that makes this water harder to freeze. So that's essentially the essence of the scientific method. And I want to emphasize, this isn't some, bizarre thing. This is logical reasoning. Make a testable explanation for something that you're observing in the world, and then you test it, and you see if your explanation seems to hold up based on the data from your test. And then whether or not it holds up, you then keep going, and you keep refining, and you keep learning more about the world. And the reason why this is better than just saying, oh, well, look, okay, I see the pond has frozen over and the ocean hasn't. It must be the salt water, and I just feel good about that, is that you can't feel good about that. There's a million different reasons, and you shouldn't just go on your gut. Because at some point, your gut might be right 90% of the time, but that 10% that it's wrong, you're going to be passing on knowledge or assumptions about the world that aren't true. And then other people are going to build on that. And then all of our knowledge is going to be built on kind of a shaky foundation. And so the scientific method ensures that our foundation is strong. And I'll leave you with the gentleman who's often considered to be the father or one of the fathers of the scientific method. He lived in Cairo and in what is now Iraq, nearly 1,000 or roughly 1,000 years ago. And he was a famous astronomer and physicist and mathematician. And his quote is a pretty powerful one because I think it even stands today. "The duty of the man who investigates the writings of scientists, if learning the truth is his goal," let me start over just so I get the dramatic effect right. "The duty of the man who investigates the writings of scientists, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. He should also suspect himself as he performs his critical examination of it, so that he may avoid falling into either prejudice or leniency." Hassan ibn al-Haytham, and his Latinized name is Al-Hazan. So he's saying be skeptical, and not just skeptical of what other people write and read, but even of yourself. And another aspect of the scientific method, which is super important, is if someone says they made a hypothesis and they tested and they got a result, in order for that to be a good test, and in order for that to be a good hypothesis, that experiment has to be reproducible. Someone can't say, oh, it was only a certain time that only happens once every 100 years, and not that's why it happened that day. It has to be reproducible. And reproducible is key because then another skeptical scientist like yourself can say, let me see if I can reproduce it. Let me not just believe it because that person looks like they're smart and they said that it is true.